Okay, well, thank you for joining us in this continuing discovery track. And we now welcome Michael, who is one of our senior principal scientists at Simulations Plus. And Michael does a lot of work focused on data science and model building. And today he'll be talking to us about AIDD, so AI-driven drug design, and on the application of external models to the AIDD problem. So before we start, I would like to deploy a quick poll. Um, are you currently using an AI-based drug discovery solution with a generative chemistry component? I will launch the poll and give you about 30 seconds or so to respond. All right. I think I will now retrieve the poll. And it looks like actually for the most part, about 2/3 of our attendees or so have not really yet deployed this kind of solution, which is going to make it pretty interesting. So without further ado, Michael, the floor is yours.
Thank you, Eric. Hello, everyone. Thank you for attending my presentation on using external programs in our artificial intelligence or AIDD module. So first I'll provide an overview of the AIDD module. Then I'll discuss some of the details of setting up the AIDD program to accept results from an external program. And then finally, I'll show an example of using AutoDock as the external program. So I'm going to turn off my cam and go over to this address here. So I first want to thank my co-authors, David Miller and Marv Waldman. So the AIDD module, the goals for the design are to produce compounds with high potency and selectivity, the primary target, have high synthetic feasibility, and then good ADMET and pharmacokinetic properties. So the pharmacokinetic properties will be calculated via the HTPK module that Dave Miller talked about earlier today. And it can be used in various phases of the lead discovery process, so hit finding, lead optimization, and then scaffold hopping. This next slide is simply an overview of the AIDD workflow, and you're going to start building a knowledge base, and this knowledge base will increase as the project increases. So initially, maybe you'll have an APO enzyme that you'll dock structures into, and then when you start making and testing compounds, you'll start establishing some SAR information. Maybe you'll have a co-crystallized ligand, and then developing QSAR models. And these QSAR models and the SAR will be improved as the project proceeds. The first thing that the AIDD workflow does is it uses starts with a seed molecule. Now this can be a single molecule or it can be a set of molecules from previous runs or just candidates you want to optimize. The next step is to generate candidates. So we do this by applying Smirk's transformations to randomly selected compounds in the population. Once a compound is created via the Smirk string, it checks a scaffold query, and the scaffold query or the compound has to meet the scaffold query or the required substructure. And this is where you kind of introduce SAR. And if it doesn't meet this substructure, then it has to generate another compound. Similarly, when it generates a compound, it checks a drug-like filter. And if it matches things such as acetals or Michael acceptors, things you wouldn't want in drugs, then again, it would generate a new compound for that. Now, you can modify both. You can modify the drug-like rules. For example, I talked to a client some time ago that they were interested in making Michael acceptors because they wanted the compounds to bind, covalently bind to the active site. So of course you can drop that particular smart string. Now, once the candidates are generated, we need to score them. So we can use our activity model to score them. We can use external programs now, and we have a synthetic feasibility measure. We can use our ADMET properties that are available throughout ADMET Predictor. Specifically, we typically use ADMET risk. And then finally, pharmacokinetic properties via the HTPK simulation module. And what I'm going to talk about today is this using external programs. This was added to ADMET Predictor in the last version, or the current version, APX3, that was released last fall. Now, once you have the compounds generated and scored, we use Pareto selection to select compounds on the Pareto front. So these are the compounds with the best properties, mix of properties of these various scoring functions. And then we simply iterate. So we generate, take everything from the Pareto optimization and then apply the transformations to them and go round and round. This next slide shows an image of the first dialog box from AIDD. And so we're looking specifically at computing objective properties using this external function. So you would click on this button here and then click to browse to a parameter file. And the parameter file specifies the uh, different variables that are used in the calculation. So this next slide shows some of the examples or variables within the external file. So the first thing is a file path alias. So you set this to a specific working directory. Typically, I set it to the AIDD output directory. And so we define a path variable. It's closed in square brackets. So then you can use this to point to different files in the parameter file. Next, we select or have to specify a command line variable, and this is either a script. It can be a bash or a bat script. It could also be a C executable program. Next, the parameter file points to a structure file. So this is the variable, and then you set it to file name. Typically, you'd include the path on that, and it can be either an SD or a SMILES file. So this is generated by AIDD. These are the candidates from each iteration. Then you can also output parameters from ADMET predictors, such as S plus log P or other descriptors, and they'll come out in this file, and maybe your script would use those parameters. Next, we specify the value of an output file. This is the name of a temporary directory, or excuse me, a temporary file, and can contain one or more objective functions. So this is created by the external function. So the external function would process these molecules and then output this output file, and there has to be one line per structure. If you have multiple objective functions, those would be tab separated on the same line. And so once this script finishes, it returns control to AIDD. It checks this output file and makes sure that there's a line for each one of the compounds that it outputted. If not, it would stop, so there'd be some kind of error, and then this file and this file would stay around. If it worked fine, then it would delete both these files to get it ready for the next iteration. And then finally, you also have to specify an objectives list and an objective maximum or minimum. So this is the name of the objective function. In my example, I called it AutoDock underscore score. So that's the name of the objective function that's returned back to ADMET Predictor. Excuse me. And then for each one of these objective lists, you need to say is a minimum value or a maximum value is preferred. So either 0 or 1. And these can be comma separated if you include more than one objective function. So now I'm going to start delving into a demonstration. I just want to recognize some of the programs I used. The first one is AutoDock. This was used to dock and score the molecules. Comes from this publication in computational biology in 2015. So this is AutoDock's been around for a while. I think this is one of the more recent releases and includes the ability to have flexible receptors, so rotate bonds in the receptor. Now, I didn't use that particular option, but it's available in this code. And then Yacera I use to process the PDB files and the ligand file in order to generate input for defining the target structure. And then I also use this to kind of look at the poses. Babel was used to convert between different file formats. All three of these programs are freely available on the web, and it was very good working with them. And then I'm going to be docking into the 6FGY crystal structure. So this is from PDB, and this is from the bioorganic and medicinal chemistry letter reference. And it's for crystal structure base 1 with a co-crystallized enzyme or ligand. And then I want to reference this article from Rambots et al. So this is what I'm going to do is kind of a retrospective study here where I'm trying to reproduce some of the compounds that they generated in this article. So the overall AIDD workflow, so this is basically the external program. AIDD is going to create an SD file with the candidate compounds in it. And then this script will take control. It's a Python script, and it converts the compounds to their dominant microstate. And this simply uses the ADMET predictor command line and the computational chemistry workflow to produce the proper charge state of the molecule. These all contain an amidine ring, which or an amidine moiety, which typically will be protonated in the receptor. Then these compounds are converted to 3D. We have a new 3D program that'll be available in the next version of ADMET Predictor, which David said should be out in April of this year. And I'll take the next two slides to talk about that, but it uses the ADMET Predictor command line and a command line script. Next, these compounds are run through a program called prepare_ligand. This defines rotatable bonds and charges within the molecule, and that's the input into AutoDock. And then I use this ADFR executable, which docks the compounds into the active site and then produces a score for each one of the ligands. Then the script extracts that score, and we can apply what's called a capping value via the script before it writes out the final set of objective results. So then it creates this output file, and that's sent back to AIDD. Okay. So I just want to briefly describe this 3D structure generating tool that's going to be available in the next version of ADMET Predictor. It's run from, you can run it from a parameter file, and that's what I'll demo here, or I used in the process here. So you just use the ADMET Predictor executable and then specify all the parameters in this file. You can also specify parameters on the command line. There's structure file and output file. These are parameters in this, but I can add that to the end of the command line and then specify the input and output file. And of course, that's easier than going and editing this file. The program is multi-threaded, so you can use multiple cores or multiple processors with the program, and it generates the structures very, very quickly, even cyclic macrocycles. It works very quickly on. There is an option to create multiple conformers with this. Now, I didn't use this in my docking, but you could generate multiple conformers of different rings and different rotatable bonds, and then you could dock those kind of statically into crystal structures, for example. You can also it also has an option to use the Merck molecular force field to minimize the structures, and I did use that option in my template file. And then finally, you can specify the 3D coordinates of a ring system in order to generate a specific conformation. I'll kind of illustrate that on the next slide. So I'm going to be docking compounds with a moiety called a dihydro-oxazine ring in it, and that's shown down here. The oxazine is basically a six-membered ring containing nitrogen and oxygen, and typically oxazines would have two double bonds in it. These only have one, so it's a dihydro. And most 3D conformer generation programs will generate the conformation of this ring kind of in a a chair conformation where this oxygen atom points down away from this phenyl ring. So I think OpenEye and Carina would generate that, as well as our program generates that structure. But if you look at the 3D crystal structure of the 6FGY that contains the oxazine ring, the oxygen points up here. So the way the program works is that first you create a template, and you create this template by analyzing an input file. So this is another command line script, and it would output a template file that would include the geometries of the rings and the smile string associated with each ring. And then when you use this template file, and it would also generate the coordinate or use the coordinate, extract the coordinates from the structure file. And then when you use this template, it searches for a particular smile string. If it finds that in the compound, then it applies that template. So this is the structure coming out of our 3D structure generating program. As you can see, the oxygen atom points up, and then I also minimize the whole structure here. Okay, so now let's kind of uh, demonstrate the program here. So I'm going to start with a seed molecule here. So this is kind of the warhead, basically, of some of these base 1 inhibitors. And note we have to specify the chirality of the compound, and we've got it in the uncharged state here. So then I would click on the AIDD module button here, and then I'm going to define synthetic feasibility, oral bioavailability, ADMET risk, and BBB risk. So the synthetic difficulty or synthetic feasibility, the lower the score, the easier it is to make. And I'm going to apply a capping value here of 2.5. And this just avoids really simple compounds from being generated and always being on the Pareto front. So anything that has a synthetic difficulty below 2.5 gets reset to 2.5 so that all these molecules kind of would be on the Pareto front. And you're not just biasing towards compounds that are just really simple to make. I also ran this with a capping value of 90 for the oral bioavailability. And typically I would increase the dose to 100 milligrams just so that really low soluble compounds might have a lower oral bioavailability. Then I'm using the ADMET risk. This contains the absorption risk, toxicity risk, and metabolic risk. And then this BB risk is something that Marv Waldman came up with. And what it incorporates are 3 areas of blood-brain barrier risk. So the first one are our models for BBB filter and log BB. The second one is the fraction cationic. The paper I referenced earlier stated that if the compounds have too high a pKa, that results in a bad distribution of the molecule in the body and also tends to be more of a PGP substrate. So they wanted to reduce the positive charge on the ligands. And then the final one is the um, if it's a PGP substrate, it would also be penalized for that. And then I would click on the compute objectives and then browse to my directory, and I just create some support files, and then I specify this AIDD parameter file. So let's take a look at that parameter file here in Notepad+. So this is the kind of a template that's provided in the ADMET predictor folder. And so the first thing I'm doing here is setting a file path alias. And this is the directory I'm going to specify at the very end of the AIDD wizard. So this folder doesn't have to be created yet, but I'll create it when in the final step. And then for the command line, I'm just executing a bat script. Here I put the full path name on this, and I'll show that bat script here in a second. And then AIDD is going to write out a structure file. Here I'm specifying the path variable that I alluded to earlier. It's going to generate a file called candidates.sdf. If this was a smiles file, there's other options for that smiles file. And then here I'm specifying an objective function. And let's see, there's some kind of ringing here. Okay. Um, then I'm going to specify an objective list here, or excuse me, the AutoDock score. So this will be the name of the objective function in the output file. And then also I'm going to uh, lower values are more favorable. So this gives a kind of a delta G or something, and you want lower values here. And then the bat script is very simple. We just change directories to AutoDock, the output file or the output directory for the AIDD run, and then it executes this AutoDock.py script, which I'll briefly talk about here. So this is a script I wrote, so you're responsible for writing the script or the program, and it basically just sets up the run, defines some variables here. We also specify a capping value. So if the score from AutoDock is below -8.1, then it resets it to -8.1, and then generates the microstates down here, and then generates the 3D coordinates, and then docks all these molecules here. Okay. Uh, so going on to the next step in the wizard, here's where you specify your scaffold query. So I'm going to load this from a file, and basically what it's doing is it specifies that you've got to have this NH2 and this oxazine ring. These carbons have to have two hydrogens attached to them, so it's not going to start derivatizing the molecule in those two positions. And then this phenyl ring has to have two carbons with that are bound to two other heavy atoms only, so you can't substitute there. And then it can substitute anywhere along these three carbons. Then what I'm trying to do with this study is kind of look at try and get the shape right in this kind of preliminary study. And so I'm allowing the substituents ortho, meta, and para. And then I'm also in this drug-like filter, I'm using the standard drug-like filter that we include in the ADMET predictor tree, but I'm also specifying um, uh, the the substitution on that ring. So that's done by this query here. And so if AIDD generates a compound where there's two substituents here, ortho and meta, on that phenyl ring, it rejects it. And then here's ortho and para, and then meta and para, so that I only allow one substituent on that phenyl ring. And then I'm going to try and let AIDD suggest the best place to put that. Um, then I would go in and specify the transformation rules. And in this particular example, we did add a couple new transformations, and these will probably be in the next release of AdMap Predictor. And you can simply add these to the bottom of the file. Those are encrypted. And then I also specified, I'm turning off some of the transformations. I didn't want to make any iodine containing molecules, so I turn that off in the transformation. You can do that in this dialog box here. And then typically I would set it up for 50 iterations, generating 25 candidates per iteration, except for the first one, and would generate 50 in the initial population. And then I would go and browse. The way I set this up was I use this AutoDock 13 directory. Now, this needs to be an empty directory. So if I would go ahead and run this, it would, throw up a caution that there are some molecules in there that we need to address. Okay, so um, first let me, so in one of the runs, I'm just showing the output here of the AIDD run. So this is the spreadsheet that's output or returned from AIDD. And once the program runs, I go into the folder where all the results are shown, and I create the script, the Python script creates a subfolder for each one of the AIDD iterations. And this holds all the AutoDock results and input files. And then I also run a script that extracts all the scores for all the molecules. And I didn't mention earlier, but I not only create the AutoDock scores file, but I also create one that contains the molecule IDs in there. And then so I read that back into ADMET Predictor, and then I also create a file called ligand poses. And both these are imported into ADMET Predictor. So here's the raw AutoDock score. Here's the one with the capping value. And then this is points to a bat script. And any link you have in ADMET Predictor, if you click on that, it will go out and execute a program. So in this case, it takes the ligand from AutoDock, overlays it in the active site, and then I can also display the hydrogen bonds on here. So you see this is making hydrogen bonds to the aspartic acid and glutamic acid residues in the active site, and then it also creates a hydrogen bond with the amide group here. So you know, kind of going on with this, I found this pose, and this was really a nice structure here. And then I ran subsequent ADMET Predictor or AIDD runs to optimize this ring while holding this fixed. Then once I had a nice ring there, I optimized this ring, and then finally optimize the substituents on the oxazine ring. So let me go ahead and wrap it up. I see I'm running out of time here.
Yeah.
And I'll just go to the last slide here to conclude. Sorry, I'm running over, Eric.
That's all right. All right.
So actually, we can just go to the questions if there are any.
Yeah.
Or poll. I'm sorry, I missed the
Yeah,
poll too.
the poll. No, that's no great. I mean, thank you, Michael, for showing this much in a relatively compressed amount of time. So it's really nice that we could see this much during this session. Yeah, I'm just going to close the session. I would like to run a quick poll, get a sense of what, based on what you saw, how likely you would be to seek additional information about ADMET Predictor AIDD for your compound optimization needs. I'm just going to run the poll now and give you about the same amount as before, 30 seconds or so, to let us know. So we realize it's a pretty hot topic. There's just so many discussions in the field right now about AI-driven drug design and drug discovery in general that I think we're okay. I will.
Yeah, I think we're I mean, we're in a good position because we've got a product. It's fairly easy to run, as you saw setting this up. So.
Well, it works now. I mean, I think that's the point. It works now. I mean, there's so many little bits and pieces everywhere, but this is truly integrated within ADMET Predictor, except for the external scoring which you showed. So it's pretty cool. I'm looking in the Q&A pane. I don't see any questions. So if and we have about I think about 60% of our audience is really liking what you that's saying they're likely to seek additional information about AIDD, which we love to hear. So thank you so much, Michael, and I'm going to close the session now and hope to see you in the next room.
Thank you, everyone. Bye-bye.
Thank you.